for this talk. And I also am sure.
Yeah, there is some.
So, the title of the talk is, if I remember correctly, Generalized Path Structures in Graphs. And I'm pretty sure that everyone here knows what a graph is. So let me just draw some picture. Basically, there are two notions of graphs which are widely well known, and these are the so-called directed graphs and undirected graphs. And I will be talking about some possible generalizations. First of all, let us introduce the crucial notion for us, the notion of a walk. What a walk is. So a walk is merely a sequence of nodes and edges. So you have some starting node, then you have first edge, then you have second node, and so on. And at the very end you have your last edge and your last node. But obviously not every such sequence forms a walk. We have to impose some constraints. The first constraint says that for each edge, let us consider ith edge. This ith edge connects to nodes, the nodes which are preceding to this edge and the node which is following to this edge. So this edge connects I believe these two nodes. And the second constraint heavily depends on what type of graph you are currently looking at. And if you are looking at an undirected graph, well, actually there is no second constraint at all. That is, you may consider arbitrary sequences, and the only requirement is that every edge connects to neighboring nodes, neighboring in the sense of this sequence.
So just a path which goes from somewhere on.
I'd better not use the term path because I would like to reserve it for a bit different notion. And it turns out that in practice we're not much interested in walks, in general walks. We are more interested in paths. And a path is just an edge simple walk. Well, it's clear that the notions of reachability, if we take them with respect to walks or paths, are exactly the same. So if some node is reachable from another one by a walk, it is at the same time is reachable by a path. You can always remove that cyclic part.
But you require only edge simple, so for some reason you're allowed to go in the same way.
For some reason I allow nodes to be occurring several times. But yes, in fact, we can even strengthen this requirement more and require node simple paths, but let's just not do it right now. So in case you're looking at undirected graphs, there is no second requirement at all. Let us say that no. Okay, let's look at directed graphs. What is a walk in a directed graph? Well, obviously it's again a sequence of nodes and edges, and they should be alternating, but there is also a non-trivial second requirement. That is, if you are looking at some particular node in this sequence, and if you examine two edges, namely the edge which precedes this node and the edge which immediately follows this node, then you should have the following thing. You should have this edge enter this node and this edge leave this node. So you should have these directions to be drawn on our edges. Let me say that
No, but somehow it just...
Yes, it's redundant. In fact, it's somewhat redundant because we can...
when we say connect, maybe it just means that we start from one or
no. Let's don't think about edges as being directed. Let's suppose that edges are just segments without any directions.
Yeah.
And afterwards, we apply certain directions to them. So edge is just an undirected pair of two nodes, and that's all. And direction is some kind of an extra information, which is attached to that pair. So in that pair, we, I don't know, designate somehow which node is the starting node, the head, and which node is the tail of that arc.
Okay. For now, it's a kind of philosophical difference, but let's continue.
And I believe that these two notions mostly cover the things which we are used to work with, and there is, however, the third notion, the notion of a bidirected graph, which seems to be less frequently used for certain reasons. But let me explain you what a bidirected graph is. A bidirected graph, in fact, is a very simple thing. It's a non-directed graph plus some additional directional information. That is, for each edge, we consider its ends, let me say A and B, and edge connects A and B. We consider its ends and assign directions to these ends. So we draw some arrows, and for each edge and for each of its ends, there are two possibilities. So we may easily get an edge which looks like this. This is an edge which leaves both of its endpoints. And we can also have an edge which, I don't know, leaves one endpoint and enters the another one. In some sense, it's an ordinary directed edge because it leaves one and enters the another one. So, if we consider this type of graphs, then it is also possible to think and to talk about walks. And by a walk, we again mean a sequence of nodes and edges, with first constraint taken into account, and the second constraint. But the second constraint will be the following. Let me erase something. We say that for each index I, okay, sorry. Let me write it in a different way. One of these two edges one of enters the I, and the other one leaves.
Yeah, so it's easy to understand if you think about these edges as just, this connecting cables,
yes.
Male and female,
yeah.
And you want them to form a chain.
Yeah. Let me draw an example. Suppose we have a certain undirected walk, and then we apply our second constraint, so we should have something, for example, like this. So you see that at each inner node, we have two edges, and exactly one edge enters this node, and exactly one edge leaves this node. And in fact, the directions which are drawn at the very ends, so here and here, are not important at all. So we may think that this walk goes from here to here, or vice versa. It doesn't. So this is the notion of bidirected graphs. It was introduced by, I believe, Edmonds and Johnson. And they were using this framework to study some general properties of integer programming problems. They were writing down some programs which were possible to solve in polynomial time, and they were explaining the meaning of these programs in terms of these graphs. To make it somewhat more clear why we need these graphs, let me just give you a very simple example. Of course, it's not the only possible one, but it indicates some peculiarities. There is a classical problem which is called the maximum matching problem. And if you consider a graph of a general type, not necessarily bipartite, and if you consider a matching in it, well, suppose this edge and this edge. Let me extend my graph. That's it. So the both edges indicate a matching. And it's a natural question to ask if your matching is maximum. Not by inclusion, of course, but by cardinality. And the classical answer to this question is that your matching is maximum if and only if it doesn't meet any augmenting paths. That is, you cannot draw a path which is not simple, which starts at a node that is not covered by a matching, for example here, and which ends at a node which is not covered by a matching, for example here, and which is alternating in the sense that it first goes along an unmatched edge, then along matched edge, and so on. So in this graph, it's obvious that there is an augmenting path, namely the path which goes this way. And it turns out that in general case, it's possible to describe the set of these paths by applying bidirected graphs. In a very simple way, if you have a graph, an undirected graph, and a matching, you may assign directions in the following way. Let us assume that every unmatched edge is directed so as to leave both of its endpoints, and every matched edge is directed so as to enter both of its endpoints. This way, leave, enter, leave, no. And again. So this way we turn our graph with a matching into a bidirected graph, and a simple path in this bidirected graph exactly corresponds to augmenting path in the original graph with respect to the original matching. So that's why studying the properties of these graphs is somehow important, and also developing algorithms that look for these paths is also important. But unfortunately, the things which happen to bidirected graphs are not so easy as we have in case of ordinary graphs. In case of ordinary graphs, the notions of reachability along a walk and reachability along a path are exactly the same. If you can reach something by a walk, you can always reach the same thing by a path. But in case of bidirected graph, it's not the case. For example, here, yeah. So here you can reach T from S, or vice versa, by a walk. You may go this way. It's perfectly clear that at each node you have exactly one edge entering your node and leaving your node. But there is no way you can avoid passing through this edge twice. You cannot make a shortcut here. Because if you cut this part of your graph off, then what you get is merely two edges. And you cannot pass through this node by these two edges because both of them enter your node. Well, it's well known that a similar thing can happen if you are looking for augmenting paths. These things are called blossoms in graphs of general type. And here is another example of a blossom. Well, but still, there are some good algorithmic news. And the news is that there is an algorithm which is due to Goldberg and Cardano, and which checks for the existence of a edge simple path in a bidirected graph in linear time. We need some assumptions about the model of computation. It should be a RAM model, but still the linear time is achievable. And what I'm going to talk today is to show you that these notions can be generalized even further. And let's look. Great.
Become completely abstract.
Yeah, become completely abstract. Suppose that you have a graph. Let us suppose it's just an ordinary undirected graph. If you have an undirected graph, you already can have the first property. You can be talking about walks, and you can be talking about edges that connect certain nodes, and everything is perfect. But what you need is some notion of the first property. And if you look at all possible versions we have seen so far, then you can easily notice that all these notions are very local. They deal with edges that are incident to certain nodes. So for each node you have some sort of a requirement. Certain pairs of edges are allowed to occur and certain pairs of edges are not allowed to occur. That is, if you are working with undirected graphs, then every pair of edges is allowed to occur. If you are working with directed graphs, then, well, one of your edges should be entering your node and the other one should be leaving. And if you're working with bidirected graphs, exactly the same thing should happen. One of your edges should be entering the node and the other one should be leaving it. And this motivates the following extension, the following generalization. Let us say that we have a fork environment. In Russian it is called vilichная среда. However, I've heard this term only twice in my life. So I'm not pretty sure.
Both times you use it yourself.
No, that was the third time actually.
Yeah.
So, fork environment. What is a fork environment? It's some additional information attached to an undirected graph. That is, for each node, we examine the edges which are incident to this node. Usual notation is delta of V. And certain pairs, undirected pairs, unordered pairs of edges here are called forks. So a fork is merely a pair of edges, distant edges, which is a subset of all edges.
So just a binary relation of compatibility between the cable ends.
Let us call fork at V. Matrix 3. So a fork at V is just some pair of edges which are allowed to occur in your walk. And clearly, this new notion covers all existing ones. There is one.
Each edge should be in some fork?
No, it's not required. So perhaps you can have some redundant edges. It's perfectly okay. But there is some peculiar situation, because in undirected case, it might seem normal to have a work which, for example, takes this edge, then this edge, and then this edge again, and finally another edge. So the question is, if we are to allow, should we allow these pairs to be singletons? That is, should we allow E1 to be equal to E2? And let us forbid this case. Well, the motivation is the following. It will make our demonstration simpler, and at the same time, we are actually interested in paths, not arbitrary walks. So we have to forbid these cases anyway, and that's why. Let's not be worried about it.
Okay, so we cannot connect the cable with itself.
No, we cannot connect the cable with itself. Okay. So, a natural question is if we can present some algorithmic or graph theoretical results here when you have a general fork environment. And the answer turns out to be positive, yes. In fact, if you are given a description of a graph together with the description of the corresponding fork environment, that is for all nodes, you have a list of all possible pairs, then it's possible to decide, in fact, in linear time, if the size also includes the description of our fork environment. It's possible to decide in linear time if we can reach one node from another by an edge simple walk, by a path. Moreover, it turns out that this notion of fork environment is no more general than the notion of a bidirected graph. So we can reduce a general fork environment to a bidirected graph. Let me explain how this can be done. In a very simple way, in fact.
So just first, if we look at this problem, is it clear that it can be done in polynomial time, or it's already non-trivial?
Not clear. It's not clear. It's no more clear than the same question being asked for bidirected graphs.
Yeah.
And for the case of bidirected graphs, it's not trivial.
Yeah.
To see that we can decide in polynomial time if we can reach A from B and without passing through any edge more than once. It's not trivial. Okay. So another way.
So let me just try to understand the picture.
Yeah.
So there was a notions of graphs, directed graph and bidirected graphs.
Yes.
And so so what you want to explain? What is your main topic? Is that you invented this
No, not me,
extension.
not me.
Or somebody does matter.
I believe it was first invented by Karzana.
Okay, you don't want to take the responsibility, but
Yeah.
there is a notion of this fork environment,
Yeah.
and then there is a reduction for the fork environment.
There is a reduction
connectivity
from
to bidirected graph
yeah.
connectivity.
Yeah.
So if you have a complicated structure of incompatible cables, you can consider a different structure with more simple male-female cables, which will be solvable at the same. But in the same graph or in different graph?
Of course, we have to augment our graph somehow.
Yeah. So you got like a different graph.
A different graph.
Problems are. So this is the main thing you want to
Well, the main thing
for a while.
Yeah, for a while.
Yeah.
At least for a while. And
So
in fact,
this is what is happening now.
In fact, the reduction is rather simple. But first, let's look at an arbitrary fork environment from a bit different point of view. A fork environment is a graph, an underlying graph, so-called, and yes, as I was saying, plus an additional fork information. A fork information can be represented by a collection of additional graphs, because we can represent our fork relation by using graphs. That is, for each node, we have an auxiliary graph where nodes of this auxiliary graph are exactly the edges that are incident to V. So here we have E1, E2, E3, E4, and E5. And here we have 5 nodes. And some of these edges are connected here. And this link, this connection, indicates that you can have the corresponding pair of edges occurring in your walk sequence. So this is some relation represented by a non-directed graph. So a Fock structure is just a collection of some additional graphs attached to our original one. Is this clear?
No,
Yes.
no.
No, at each room we have some cables which come to this room, and we have a need to write down the information which of them are compatible.
Yeah.
What we do, we just draw a line between the end points of the cables which are compatible. So now the connection is now somehow distributed, represented by a line and two cables.
Yeah, but these edges in the G
In GEV?
in GV should be directed.
No, why so?
No, it's
A fork is
if
non-directed.
two cables are connected, are compatible, they are compatible in non-directional.
No, there is no direction here.
Yeah, and of course we cannot make any use of, for example, the connection E1 goes to E2 and then to E3.
No,
it's completely
it's not
useless for us.
transitive, no.
Just we need the lines.
Yeah. Okay, and let us do the following thing. Let us take all these graphs and embed them into our graph G. That is, we do the following. We replace each node of G by the corresponding graph. Well, suppose that you had something like this. You had two nodes, U and V. So now we have two subgraphs.
So it's a regional graph on the top, yeah?
On the top is the original graph. Now we are taking graphs G, U, and G, V, and we are placing these graphs in place of our original nodes. Here we have to have 3 nodes, and here 4 of them. Well,
So under the microscope, each vertex infects a group of things.
yeah. So each node here is replaced by the corresponding graph. And if you have an edge which connects U and V, so that's U and V. E1, E2, E3, E4, E5, and E6. That would be here E1, E2, E3. Here again, for example, E3, E4, E5, and E6. And we connect the nodes of these graphs if these nodes are the endpoints of the same edge in our original graph. So in fact there should be an edge going here, which corresponds to this link. An edge going here, 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 and here. And finally we assign directions. In a very simple way, each edge which is inside of one of these graphs is directed, for example, to leave both endpoints and if you have an edge connecting these clusters, then you direct it to enter both endpoints.
Yeah, so the only way to use this internal edges is just to connect some external edges because they don't match anything else. So what we do is exactly what we want.
Yeah. So if we consider a walk which is admissible with respect to a fork environment, then this walk can be easily translated into a walk in our newly created graph. That is, we use external edges which correspond to edges of our original graph, and then we intermix them with edges going inside clusters. And the choice of